Hey guys, welcome back. This week's assignment is going to be learning the hexadecimal numbering system. And I should have wrote there, this is base 16. So this is pretty similar to octal or binary, or anytime we're converting between numbering systems, the process is really the same. And actually, you guys used the hexadecimal system freshman year with Mrs. Hawk when you guys were talking about the color palettes. I think, pretty sure if you guys reach back and remember, you guys talked about, 1A or, 3F. Those are hexadecimal numbers. So before we get started into how to actually do the conversions, which I think are going to be a little bit of a rehash for you guys, what I want you guys to do is just write down this numbering system. It's going to help. So we have the binary, or I'll just say base 2, right? And we have 0 and 1. And we have octal, or base 8, which is 0, 1, 2, 3, 4, 5, 6, 7. So 8 numbers, 0 through 7. We have our decimal system, base 10. And again, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. 10 numbers, 0 through 9. And now we're going to learn hexadecimal, or base 16. And again, we have 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. What happens is we don't go to 10. 10 in base 16 is not the same thing as our base 10. So what we do is we use letters, and we go A, B, C, D, E, so 10, 11, 12, 13, 14, all the way to F. So I would write that down, write it better than I did. Obviously didn't space out enough, but I would put next to these, this is equal to 10, it's equal to our 11, this is equal to our 12, it's equal to our 13, it's equal to our 14, and this is equal to our 15. These really help me. I don't memorize that D is equal to 13, so I use a system just like this when I do my numbering systems as well. And it just really helps, so having these written out, and maybe you don't have to write all this, and you could literally just write A equals 10, B equals 11, C equals 12, D equals 13, E equals 14, and F equals 15 somewhere. That's going to help when you go to do some of the conversions. So let's just start with a simple one. We're going to go 200 base 10. We want to know, what does that equal in base 16? So again, right, we're going to draw it out. This time we're going to do 16 to the 0, 16 to the 1, 16 squared. And I can tell you, we're not going to go past 16 squared. So 16 to the 1, or to 0 is 1, 16 to the 1, 16 squared is 256. So 200 bigger than 1? Yes. 200 bigger than 16? Yes. 200 bigger than 256? No. So we can't have any 256s, the number's not big enough. So this is our 0, right? We know we're not going to have this. How many 16s do we have in 200? We know we have at least 10, right? 10 would be 160. And you might need a calculator for this. But it's basically, we have, and I'll write this out, right? A is equal to 10. B is equal to 11, C is equal to 12, D is equal to 13, E is equal to 14, F is equal to 15. And we're going to have 12. 12 times 16. So we have C, and we do 200 minus 12 times 16, should be 192. Leaves me with 8. So how many ones do we have in 8? We have 8. So 8 times 1 minus 8 should be 0. So then 200 base 10 is equal to C8 in hexadecimal. So again, it's the same process. You're just adding these now. It's a little different. And going the opposite way, I think one common mistake would be people write, instead of writing C, they would write 12. The answer is not 128. The answer is C8. That's maybe a big difference too. This would be incorrect if you wrote 12. Hey, there's 12 16s in 200. No, that's not the case. You have to write the letter C. So just be careful there. That's maybe a common error that happens. And we can go the opposite way, right? Let's say I have 1, 0, A in base 16. What does that equal in base 10? We do the same thing. 1, 0, A, we break it out. Remember, this is worth 16 to the 0, 16 to the 1, 16 squared. So this is 1, 16, 256. 1 times 256 is 256, plus 0 times 16 is just 0, plus A times 1. Well, it's not A, right? We know that A, I should have left this up there, is equal to 10. So this is plus 10. That'll be 256 plus 0 plus 10, 266. So 10A base 16 is equal to 266 base 10. So nothing super new for you guys in that aspect. This is kind of going from decimal to hexadecimal, and then hexadecimal to decimal were two examples I showed. I'm not going to do any more examples of that because I think you guys have seen it enough. But one thing I do want to show you is the nice thing about hexadecimal and octal is that you can switch very readily between binary numbers or between hexadecimal and decimal. So like I said before, if we have these big numbers, right? 1, 0, 1, 0, 0, 1, 0, 1, 0, 1, 1, 0, right? That's a big binary number. But we could represent this in hexadecimal or octal pretty readily. So if we wanted to break it down into hexadecimal, what we would do is every 4 would be representative of one hex number. So I split this here, 1, 2, 3, 4. I split it here. And now I can look at these and it's a little easier. I know that 0, 1, 1, 0, this is worth 1, 2, 4, and 8. So this is 4 plus 2 is a 6. And here is, again, just another 4-digit number. This is worth 1, 2, 4, and 8. So this is just a 5. Then here again, same thing, 1, 2, 4, and 8. 8 plus 2 is 10, but remember we don't use 10, we use A. So this whole number up top in binary is equal to A56. Now if we wanted to go to, instead of the hexadecimal, we want to look at it in octal, which is what you guys learned last week. Instead of going every 4, you just go every 3. So 1, 2, 3, 1, 2, 3, 1, 2, 3. And now just write these numbers down again. So 1, 1, 0 is still a 6. 0, 1, 0 is a 4. And obviously you notice that these would never be bigger than 7. 7 is the biggest number any 3 could be. This would just be 1. This would be 5. So it's also equal to, this is base 16. 5, 1, 4, 6, and base 8. And that's a lot easier than doing the breakouts to get the decimal, because these are all, base 2 goes to base 8 to 16, you're fine there. So you could even start with, let's say we do 3, 4, 7, 1 in base 8. I could break this, I can take this to hexadecimal by first going to binary. So I know 1 is 0, 0, 1. 7 I know is 1, 1, 1. 4 I know is 1, 0, 0. And 3 is 0, 1, 1. So now this is the binary equivalent of that in octal. And then to get it to hexadecimal, I just do every 4. 1, 2, 3, 4. And now I know that 1001 is a 9, 0011 is 3, and 0111 is 7. So this is equal to 739 base 16. And you can kind of readily switch between those. So I'm not going to have you guys do this. I just thought that was something interesting that I wanted to show you guys. And that's part of the reason we use the hexadecimal numbering system as opposed to this long binary system, right? We can convert that right to 856, and this number can go to 739 a little more readily using hexadecimal, and it saves a lot of characters in a computer system. So good luck. Email me if you have any questions, and I will see you guys on Wednesday.